In this course, Daniel Bark will teach you how to code a fully functional Minecraft clone using React, JavaScript, and Three.js. Daniel is a senior software engineer from Sweden. You will create a game that supports 5 Minecraft block types. It will include moving, jumping, switching and placing blocks, saving, and more. You will learn about many React concepts such as useState, useEffect, useRef, and custom hooks for state management. And you'll be able to apply the principles to create other 3D games in JavaScript.
Alright, so let's get on with the tutorial. And to begin with, let's have an overview of the steps we're going to take in this tutorial to build a Minecraft clone. So first we'll look through the code that we're starting out with and the packages that we're going to use. Then we'll add our first 3D element, which is a skybox that will wrap the entire world. We need some images that will be used as textures on the ground and on the cubes. Next up, we'll use a plane as the ground, and our player is going to interact with that ground. So the player is going to get a first-person view, will mount a camera to a sphere, and that will feel like a first-person game. Then we need to have some gravity. We need to make sure that the player cannot fall through the ground, and when you jump, you should fall back to the ground, and so on. We need some movement to go back and forward and to the sides. And then we need some state management, because we need to keep track of all the cubes in the world. So you need to be able to add and remove cubes in a global state. So we need to keep track of that. And then we also need to keep track of what type of cube the player wants to add to the world. So we also need some type of UI that indicates what cube texture is active. It would also be nice if we can save our world, so we don't have to start from scratch every time we come to the app. So we'll implement a button to store the world in the local storage, and also to reset the world if we want to start over. We'll have a reset button for that. And in the end, we should build ourselves something fun like a house, or we'll see what we come up with. All right, so let's look through the code that we're starting with. So we have a package JSON. So we have React 3 Fiber, the main package, and then we're going to use some nice functions from Canon and Dry. We have React, we have 3, we have a way to generate IDs, and we have the state manager useState. Now let's jump to the components folder. Is empty right now, but we'll populate it. Inside images, we have small images like this. We have dirt, glass, grass, logs, and wood. And I already created a JavaScript file that just imports these images and then exports them in an object like this. Let's go to the index. So here, not much is going on, quite standard. We have an index.css file with not much in it. I just added some helper classes, and we'll probably add some more later on. And inside the app here we have just a div that says outside canvas, and then we have canvas from React 3 Fiber, and we have nothing inside the canvas right now. So we see a text here that is outside the canvas, and the rest of the screen is covered by the canvas. All right, so we are done with looking through the boilerplate. So onwards towards the sky. So the sky we will import from, let's see if we get some help here, sky from React 3 Dry. And let's see if something happened. Yes, we got a sky. So for now we can remove this div that says outside canvas. What I wanted to show with that is that you can add normal HTML as long as it's outside of the canvas. Because if I move this into the canvas, we get some errors because React 3 Fiber doesn't know what to do with the div. It has all kinds of other primitives it can render, like meshes and geometries and so on. But it cannot handle divs. But we can place them outside, and then we can mix the 3D stuff and the normal HTML stuff. So I'll remove outside canvas for now, so we get a full view of the 3D content here. On the sky, we can set sun position, and that takes an array of x, y, z. So I'll do 100, 100, and 20 or something. It doesn't matter too much, but now we see that the sky got a bit brighter, and I cannot really look at any other part of the sky because the camera is now static. So we can adjust the sun position later if we're not happy with it, but at least now we have a sky in the day and not an evening sky like it was before. So I think we'll leave the sky like this for now and jump onwards to the next step. Alright, so let's prepare our images and turn them into Three.js textures. So first I'm going to change actually this images file so that we can destructure them when we import them directly. So I will clean it up like this. Let's create a new file and call it textures. So then we can import from images. So what we need to do here is create textures. So let's start with the dirt texture. So we need to import from Three.js the texture loader. So we say new texture loader and we give it the dirt image. So we just repeat this. There we go. And we create a separate texture also for the ground, even though we're going to use the same image. So we'll call that ground texture and uses the grass image. So now we want to export these. There we go. So now we have a file that exports the textures. So I think we can cross off textures and images. So our next step in the list is to work with the ground. So before we create the ground, let's add a few things in here. Let's add an ambient light. So that is a light that will light up every 3D surface. And that one takes a prop intensity. So let's do 0.5. And before we include the ground, we need to add a physics container because we're going to use a hook from Canon to create our plane that will be the ground. And that needs to be within a physics boundary. So we'll do physics from Canon. And inside here is where we can create the ground. So let's create that component now. Ground. Okay, so here to create our ground plane, we're going to use a hook from Canon called usePlane. So this plane will give us an array where the reference comes first, and that is a reference that we will place on the mesh that we let Canon control. So usePlane. So it takes a callback function that returns an object. So here we can set some properties of this plane like rotation and position and so on. So we'll do rotation, and here we have an array of 3, and position also an array of 3. So now we're going to return some elements here. So we will take a mesh. First we will reference this mesh. So we'll set ref is ref. And then we have the geometry. So we'll have a plane buffer geometry, and we'll attach this as a geometry. And here we can set the size of the plane with the args prop. So since it is a plane, it has 2 dimensions. So we'll set it 100 by 100. And we also need to add a material here. So we'll do a mesh standard material. And this should attach as a material. And here is where we want to add a texture. But first we can just set a color. Let's do hot pink. All right, so if we look at the browser now, we have something hot pink that is covering the entire screen. So we don't want to have color hot pink. Here we want to attach the ground texture. So let's import the ground texture. So we just say map is ground texture. Okay, so we got an error because we forgot one step in the texture loader. We need to call it and then call the load function. Okay, so we instantiate a texture loader, and on that we call the load function for each image. That's important to remember. So now we can continue debugging this. Okay, so now we have a new texture here. So as we can see, it doesn't really look like the grass image, which has these small pixels on it. So what I suspect is happening now is that the image is being stretched out. So we want this texture to be repeating. We want this small image to repeat over and over. So we can do ground texture dot wrap s, and we'll do repeat wrapping and import that from 3. And the same for t, and then we'll do repeat dot set, and we'll set this to the same as our size, 100 100. There we go. So now we have it repeating, but as we can see, it looks very blurry, and that has to do with how the texture is being stretched and essentially how the rendering engine figures out how to display these colors. So with this setting, it's like smearing them, and we can change that if we do ground texture dot mag filter nearest filter instead. So let's see what happens now. That looks much better. Now it looks pixelated as it should. So our next step would be to flatten or lay down the ground, because right now the ground is standing up. So we can play with this rotation here. So I will rotate the x-axis, and we want to rotate it 90 degrees, but in radians. So 2 pi would be 360 degrees, which means that 1 pi is 180 degrees, and half of a pi is 90 degrees. So I will do math.pi divided by 2 to rotate it 90 degrees. And it might be that we're seeing it from behind now. So I will flip it 180 degrees. So it folded over maybe so that we can no longer see it with the camera. So let's do it a little bit less. Okay, there we go. So now we can see that it lays down, but not completely 90 degrees. But for now, we can keep it like this for a while. We can see that it's almost correct, because once we can move the camera around, it's going to be easier for us to to flip it back then, because then we will add gravity and we will fall down onto the ground. But let's keep it like this, just that we at least can see that we have the ground there. All right, so we have the ground. Let's start to work on the player. So our player needs to have a camera. So we can destructure camera from a hook called use3. So that hook is from React 3 Fiber. So we also need some type of geometry to represent the player, the geometry that can collide with other geometries and so on. So for that we can use a sphere. So this will be similar to what we did to the plane for the ground. So we'll do use sphere, and we call use sphere, and it takes a function that returns back an object. So here we can set mass, we'll set that to 1. We'll set type to be dynamic, and we'll return a mesh. And attach the ref. And then let's add our player. All right. So we should have a player now. So the next thing, so we won't see that anything changed yet. So we need somewhere to store the position of our player. So let's create a variable called position, and we'll do a reference, and it has x, y, z coordinates. So we'll do 0, 0, 0 to begin with. Now we will call the use frame hook. So this hook will run on every frame. So what we want to do now is attach the camera to this position that we're going to connect to our player. So what we can do is that we can take the camera, which is from use3, and we take the position and we copy, and we pass in a new vector 3, and this vector we give position.current, and we give it the x, and then we do the same for y and z. Position.current.1, which is y, and position.current2. So now we should have a camera that follows this reference to a position here. Okay, we can set a console log here just to see that our frame is running. Okay, so we see that we no longer see the ground, and we have frame console log in here, so we can see that it runs on every frame. So let's remove this. So we did something to the camera, at least. That is good. So if we uncomment this line, we should see the ground again. And we do. So that's good. So we were able to move the camera. We copy it to this position every frame. So our next step is to have this position follow the position of this sphere, because this sphere will be affected by physics and gravity. So we can do a useEffect, and this use useEffect will need to rerun every time the sphere changes position. So we can take out element number 2 here from useSphere, which is the API, an API towards the sphere. So we'll say that rerun this effect every time the sphere API position changes. And what do we want to do when the position changes? We want api.position.subscribe, and subscribe takes a callback where we get, we'll call it p, and we'll say position.current is equal to p. So p is a triplet, so it will look like this. So now we have a sphere that is connected to this reference, or let's say this reference follows the sphere, and we can get the camera to follow this reference. So our goal is to get this camera to follow the sphere. Okay, so now I added back the camera, so we can see that something happens. We get ejected. I don't know if we may be colliding with the ground, and then to handle that collision we just get ejected. If I change the Z value here, so if I do 10 and I reload, I land on the ground. But because remember what technical depth we had from the ground, we didn't flatten it to 90 degrees properly. So now would be a good time to fix that. So like I said, to rotate 90 degrees, that is half of a pi. So now we flatten the ground out. So we fly up and then we land on the ground. We have taken the camera, we glue the camera to our position reference, and then we subscribe to API position changes of the sphere. So we have a ref that tracks the sphere, and then we glue the camera to our reference. Hopefully that makes sense. So we need to do similar things to the velocity. So let's copy this position code here, and we'll call this vel, and here we track api.velocity, api.velocity, so here we get v, and we'll set vel.current to v. So now we have a reference of the velocity that subscribes to the velocity of the sphere. Okay, so let's fix this catapult effect thing. So what I suspect happens is that when the sphere is inside of the ground plane, that state cannot exist, so we just get flung out so that there's no collision anymore. So we need to lift up the sphere a bit. So let's try 5. So now we start from above the plane and then we fall down to it. So let's see how close we can get. So if we put 1, we seem to be standing on the ground as we start, so that's great. Let's see if we can actually trigger some movement on the sphere. So we have the API, so we can do api.velocity.set. So here we can give it the x, y, and z velocities. So we can do 0, 1, 0, then we should be constantly lifted upwards. So we'll do something similar to this when we implement jumping, because then we want to set velocity upwards, but just for a short while, so you fall back down, so it's a normal jump. All right, so I think before we can move forward, pun intended, with the player, we should make a hook for the keyboard inputs so that we can register different key presses that we're going to use to control this sphere that is the player. So let's add this to our to-do list, keyboard inputs. So the player is not yet done. We'll move to the keyboard inputs first. So the keyboard input is actually a hook. So let's do a hooks folder and we'll call it use keyboard. Export const use keyboard. So we'll need to have some state here to keep track of what keys are pressed. So we'll call it movement, set movement, use state. So let's set up this initial state. All right, so we need to map out all the keys and call them things that we understand. So one action is move forward, move backward. We also have move left and move right. We have jump. And then we have texture 1, 2, 3, 4, 5. I think that should be all the... Now that we have textures, we should maybe call it actions. So now we need to have a useEffect. And inside here we do document.add event listener. Listen for key down. And then we need to create some functions to handle this. Key up. And since we're adding event listeners, we also need to return a function that removes them. Otherwise, we will add endless event listeners. Handle key down. We wrap this in the use callback. So inside here we get the key down event. So let's create some helper function to determine what key maps to what. So we'll do function action by key. So here we get a key map, key action map. So here we say key. Here we need to type it as they are called in the key event. So key W like this. We'll call it move forward, and we have space for jump. And then we have digit 1, and now we can say what texture it corresponds to. We'll say it's dirt, and grass, wood, and the last one is log. So now we mapped out what keys belongs to what actions, and then we just return key action map with key. Of course, we need to check so that we only react to the keys that we are listening for. Action by key e.code. So now we can do set movement, and of course we need to preserve the previous state. So we spread the previous state, and then we set we can do action equals action by key e.code. Then we can just say if action is true, and this is now called set actions. Okay, so it will be very similar for the handle key up. Just that we set this to false. So here we need to do handle key down and handle key up. And then we just return the actions. Let's try this hook from the player component. I'll do like this, so we'll just see those that are true. Key and value, and we return those that have true. Alright, so now we should be able to see in the console log when we press these different keys that we are looking for. Okay, so we have no actions when we start, that's good. So now I press W. Okay, so I'm not getting anything, so let's debug. Let's see if we are here. Yes, we get the keyboard event. Action by key. Action by key is a function, not a map. So this should fix that, and same thing here. So I'm pressing W, S, A, D, jump, spacebar, and the digits 1, 2, 3, 4, 5. Okay, so we have everything working. So now we can react to these actions and control the movement of the sphere by looking at what key presses we're doing. So we can cross off the keyboard inputs. All right, so let's control the player using the keyboard inputs. And I think an easy one to start with is the jumping, because this requires some vector math. So it will be a little bit tricky, but I think we'll manage it. So first we can look at if actions.jump. That means that we are jumping. We can reuse this code. Here we can, for the X, we'll just keep the value, and for Z, we'll just keep the value. And here, this is a constant that we'll use for the jumping. So let's store it. Jump force. Let's try 10. Jump force. Okay, let's try it out. Spacebar. All right, so we achieved the jump. It felt a little bit too high. And also we can jump indefinitely, which is wrong. So first let's fix the jump height. Let's try 3. Yeah, that's better. We'll try 4 for now. So we need to do another if check here, if we can jump again. And one easy way of eliminating all these extra jumps is that we make sure that our Y velocity is 0. Make sure that we're not moving up and down, because whenever we are moving up and down, it means that we are falling through the sky or already jumped and we're on our way up. So we need to make sure that the velocity in the Y direction is really close to 0. So let's do, since we care about positive and negative, we can do absolute value, and we have it on velocity dot current it's vel, right? Current one should be smaller than 0. Let's do 0.05 maybe. Okay, so let's try. Good, we can still jump. I'm pressing it continuously, but we're only allowed to jump once we've landed. There's one bug that we should fix, and that is that we can jump if we hit right in the moment when we're actually slowing down from going up to going down again. So it's the velocity there becomes almost 0 at a certain frame. So if I can time that frame, you can see that I can jump 2 times in a row. But we'll leave it like that for now. So we can start to think about how we move in a direction. And the tricky part about it is that later on we will be able to turn around. So W will always take us in the camera direction. So we need one vector to represent what direction we are facing, another vector for the forwards and backwards speed, and the other one for the side speed. So let's create those vectors. One direction vector, vector 3, and we'll call it front vector, also a vector 3, and a side vector. So the front vector, it's this Z axis here that will determine us going forwards and backwards. So both the move forward and move backward should affect this force here. So one way of doing it is we check actions.move backwards, and we set it to 1 if we're moving backwards, or 0. And then we subtract the same thing, but for moving forward. So if we press them at the same time, they cancel out. We could actually destructure here, move backwards, move forwards, move right, move left, jump. Then we can clean this up like this and like this. All right, so we have this one 1 or 0 and this one 1 or 0, and if they are both 1, they cancel out, which is a good thing, because if you go forward and then you start to hold backwards also, then you should stop, right? That's what we see in games. So then we've taken care of the front vector. So let's do something similar for the side vector. So we'll copy these. So now we're not moving in the Z direction anymore. I think this should be the X direction. And here it's move left. And here it's move right. So we get the same behavior there. If you're holding both at the same time, you should go nowhere. There we go. So now we're going to do some calculations, and we will originate from the direction vector. So we'll do direction dot subtract vectors, and those vectors are the front vector and the side vector. And then we'll chain on some more operations. We normalize, and then we multiply scalar, and here we need to determine how fast we want to go. So let's also make a variable for that, or a constant. We'll try 4 for speed as well. So we'll multiply the speed, and then finally we apply Euler. And this is where we get the correct facing direction from the camera. So we have a reference to the camera and its rotation. So this is where we make sure that the front and side vectors are correct in relation to the camera. So now we can take this direction vector and apply it to the sphere. So API.velocity.set, and then we do the direction.x, direction.y, and direction.z. But that's not completely true, because the y-axis is not controlled by these front and side vectors. This is just for moving backwards and forwards and to the sides. So the y should actually stay the same. So we'll do vel.current1. So that should be enough. In the best of worlds, we would be able to move at this point. Let's see if we need to refresh. All right, I think we're missing the new keyword here for the vectors. There we go. All right, so we have a typo here. Okay, so let's try. I'm pressing forward. All right, so forward is working. Backward is working. Now we'll try backwards and forwards at the same time. And it stops, that's great. Let's try left and right at the same time. And I let go of left. All right. So that seems to be working. So we cannot yet test that it will be still correct when we turn the camera. That we will do once we build out the pointer lock controls, where we can control the camera with the mouse. All right, so I think we are done with the player for now. Let's move forwards with the first person view. So we'll create a component, FPV. And this one is actually quite simple because we get a lot of help from React 3 Fiber here. Okay, so we need, of course, to connect this to the camera. So we need use3, where we can get the camera. Okay, so we return pointer lock controls. Args is camera. Destructuring GL here. Passing that as GL DOM element. FPV from FPV, and just render it. All right, so when I click here now, it should lock the camera to how I move the mouse. So now I can look around. So now we can see that if I'm facing left, I can move straight ahead, and if I turn a bit, I can still move straight ahead. So our player movement seemed to work fine, and the pointer lock controls seem to work as well. There's one thing we should do with the first person view, is that we should add a small cursor to the middle of the screen. So outside of the canvas, let's add a div, class name cursor, and let's put just a plus there. And let's position it absolute. And we're going to center this on the screen. So let's make a class called centered. So this is positioned absolute. So we do top 50%, left 50%. We need to add a transform, translate minus 50% and minus 50%. So that is just because if we if we center it 50-50% without doing this transform translate, then it will not actually be in the middle, because I think I can show you this. Background hot pink. So if we make this bigger, we see that it is in fact centered, but if we don't have this translate, this is what will happen. The top left corner of the square will be in the center. So what we're adjusting for with 50% is 50% of the width and height of the square. So then it will move to the middle. But this one doesn't need to be big at all, so we'll remove these two. That looks good. And then remove the background. So move the color styling to cursor. There we go. Now we have a marker to indicate the center of where we are watching. Great, I think we are done with the player for now. So we will cross out first person view. We're also done with gravity, and we are done with the movement. Our next item on the agenda is to add a state manager. We can add a hook called useStore that keeps track of the game state. So let's create our hook, useStore. So we'll need create from useStand, useStore. We can wrap this in create, and we get a setter method here as an input parameter. So we will return an object. So we call create, we pass it a function that returns an object. So in this object we can declare our state. So we need to keep track of a texture, and we can default the texture to dirt. We need to keep track of the cubes that the player is going to be able to place. So we can just default that to an array. And now we're going to declare our methods that you can use to interact with the state. So we'll of course have add cube, remove cube. You need to be able to set the texture. And for later we want to be able to save the world, reset world. These are all the operations that we need to support in our store. So when we add a cube, all we need to know is where to place it, because the texture we already know since we are in the store. So when someone calls add cube, we need to call set, and in set we pass it a callback function and we get back the previous state. So here we can return an object. So here we just want to affect the cubes, which is an array. So we spread in the previous cubes, and then at the end we add our new cube, and every cube needs to have a key, and then we can use nano ID for that. We have a position that we get from XYZ that's being passed in, and then we have the texture, which we can get from prev. So that should be all it takes for us to add a cube. But before we do that, we need a way to render cubes. So I suggest that we leave the store like this for now, with just a method of adding cubes. And then we create the component to render a cube, and then we can start to render them out. We can actually initialize the state with one cube just for debugging. Let's do 1, 1, 1. So now we always have one cube initially that we can quickly see if when we start to rendering the cubes, if they come out. So I suggest that we leave the store like this before we finish the rest of the store functions, and then start to working on rendering our first cube. So let's add a new component. Before we create the cube, we should have a component that is taking care of rendering all the cubes, essentially consuming the store and mapping out the cubes. So we'll make a component called cubes. So we need definitely to have the use store from hooks. So our use store hook, we get the state back, and then we can return an array where we can place different things from the state in whatever order we want. So we want state.cubes. So then the first element here will be the cubes. So if we do console log cubes, we can return nothing here. Let's add cubes. So since the player needs to be able to stand on the cubes need to be within the physics. So add it like that. Okay, so we consoled out the cubes, and this is our debugging cube that we added. A dirt cube on position 1, 1, 1. So now we can start working on mapping out those cubes. So we return here we're going to use the cube component. So let's create that one first. Since we're doing a mapping, we need to use the key, which is something that we have on the cube already. We have key, we have X, Y, Z texture. So here we can use the key. This is actually position. So we receive position and texture. So to create a cube, we're going to use the Canon use box hook. So we'll set type is static, and we have the position from the incoming prop. So here we return a mesh, and to the mesh we connect the ref. Here we need a box buffer geometry, and we also need a mesh standard material. Attach as geometry. Color is hot pink. Do we have a cube anywhere? Okay, so I see we called it position in the store. And here we're destructuring position. So we need to call it pos here. Oh, okay. So the reason I couldn't find the cube was because I was standing on it. I feel very stupid now. But that's good. So let's play around with these values. See if we can get it up in the air. All right. So there we have our first cube. Right, so we have the cube standing on the ground. So now let's fix the texture of the cube. So let's pass in the texture. In the store, we just call it dirt, and in textures, we call it dirt texture. So let's do texture plus texture. So we import all the textures as textures, and then we map it by the texture in the store plus texture, and then we get our active texture. Then we can do map active texture and remove the color. There we go, we get the dirt texture on the cube. Let's move it a bit closer to us. So as we can see, it doesn't look so good. So we need to do the same treatment we did to the grass to every cube texture. So we'll test it with dirt texture, mag filter, nearest filter. Let's see if that helped. Yeah, now it looks good and pixelated and not smooshed. Let's do it to ground texture in here as well, since we are already here, and then we don't have to do it in here. Let's move these out as well. There we go. So now we fixed it for all the textures inside of the texture file instead, to keep our components more clean. I was thinking to maybe keep this in ground because it correlates to the size of it. So we'll keep it here. So now we should be able to add a second cube with another texture. And we'll pick another position. Texture wood. Alright, so now we can render cubes with different textures, and this one looks nice as well since it's been fixed. Alright, so now we have a way of rendering cubes once they are added to the store. Alright, so we have the basics of the state management, and we have the cubes basics as well. Something that is missing in this list is adding cubes. So one way of adding a cube is to click the ground. So let's open the ground. So we need to get the add cube method from useStore. Add cube. And we return an array with state.addCube. Alright, so we have the add cube method, but we need to figure out the x, y, and z coordinates to pass to this function. So let's add an on-click to this mesh. Let's do e.stop_propagation so that the click cannot be passed through the ground. So on the event we have something called e.point. So we want to get x, y, and z. So we can do object.values from e.point. So let's stop here to check out what happens when we click the ground. So we have E. Let's look at point. So we have a vector 3. So we just want to get the values of this vector. We don't want to pass the whole object. So if we do object.values, we just get these 3 values and we destructure them out here. So if we hover the x, y, and z, we see that we do in fact get the values here. As you saw, there are a lot of decimals here. We want the cubes to end up on fixed location according to this grid that we can see here in full numbers. So we need to round this. So we need to do a mapping of these values and return math.ceil of the value. And then we should be able to call add cube with x, y, and z. Alright, so let's try this out. Let's reload, and we click the ground, and we do get a cube. So as we can see, the ceil function made it round up, so let's try with floor instead. So as we can see, I think we should try moving the ground down by half a unit and see if that will make the cubes lay flat on the ground. So let's try that. So now that we fixed the ground, we can go back to ceil here. Math.ceil, and when I click the ground, we actually get cubes added. Pretty cool. So now let's lower these default cubes, or we can actually remove these default cubes now that we have a way of adding cubes for real. Okay, so we handled the case where you click the ground and you want to add a cube. But what about when you click the surface of a cube to add a cube next to it? Okay, so let's handle the clicking of cubes. So we can copy this state call here because we want to do the same inside of cube. But we also want to have remove cube later on, so let's add that straight away. So my plan is that if you hold in a modifier key and click, then you can remove cubes as well. So let's add an on click. We stop propagation. So here we need to handle a few things. A cube has 6 sides, and the side that you actually click needs to get another cube next to it. So we'll create a variable clicked face, and a face of a cube actually has 2 triangular shapes that covers the face. So it's not a full square, it's 2 triangles that together cover the square face. So instead of 6 faces, it has 12 faces. But that is pretty easy to fix. So we can just take e.faceindex and divide it by 2. And then we will be in the range between 0 and 5 instead of 0 and 11. And we will of course need to math.floor it, because there's no 0.5 face index. So now clicked face should be between 0 and 5. So let's console log face clicked face. So let's add a cube here. Phase 4, phase 1, phase 5, phase 0, top is phase 2, and the bottom should be phase 3 then. So now we just need to write if statements to cover all these clicked faces. So if it's 0, add cube. So we have a ref to the box that has a position, so we can do x, y, z from ref current position. So we can pass in x, y, z, and then we need to, on one of them, maybe subtract 1 to the x. And for another phase we need to do x plus 1. But it's a little bit of guesswork to figure out what phase is what direction, if you understand what I mean. 1, 2, 3, 4, 5, 6. So something like that. This will most likely be wrong. All right, so we add a cube, we click one face. So here we see that it was the opposite. All right, so now we have logging as well. So if I click this face, we see that it was 4 and the cube was added on the other side. So clicked face 4 just needs to flip. And then let's flip this one. If I click this face, that was face 1 and that was also flipped. So this should probably -1 and maybe +1 here. Let's try the top. So phase 2, nothing happened, so I'm suspecting that there's a cube underneath. So this should probably be +1 and this should be -1. So let's try again to click the top. Yeah, now that one was correct. So I think we might have it. Nice. Now we can click a cube to add another cube next to it. So now it starts to become fun. So we can return if we are done with the operation. So now we can handle the removal of cubes. If e.alt key remove cube x, y, z and return. And of course we haven't implemented the remove cube function yet. So what we can do just to try it quickly is to just console log here. X, Y, Z, X, Y, Z. Remove. Alright, so I'm holding down the Alt key and I'm clicking it and we get a call to remove cube with X, Y, Z. So that's great. So now we can implement the remove cube function. So we can borrow some code from add cube. We'll still call set, but instead of adding to this array, we can take prev.cubes.filter cube, or we keep all the cubes where X, Y, and Z are not equal to the X, Y, Z being passed in. So we destructure X, Y, and Z from the cube. Then we return X not equal to X, Y not equal to Y, and Z not equal to Z. So let's see if we can filter out the cube that we're clicking on. Let's add a few. So here we need to say cube.pos. All right, let's try again. So add a few cubes and then Alt key, and they were all removed. I think the issue is that this should be OR, because if any coordinate is not correct, it's not the right box to filter out. So let's try again. There we go. One cube being removed at a time. Great, now we can remove cubes. Great progress. All right, so we are done with adding cubes and removing cubes. So let's continue with the cube type selector. So we should create some UI that indicates what selections there are and what is currently active. So let's create a component texture selector. And this one will not be a 3 component, this will just be HTML. And this one should just be visible when we're actually changing the texture. So we need some state here to determine if it's visible right now or not. We'll default it to false. We need to get the texture from the store, active texture. State, and we get an array back where we take state dot. We just call it texture. Texture. So let's create a useEffect that runs whenever the active texture changes. Active texture. So if the active texture changes, we want to have this texture selector visible for like 2 seconds, and then we want it to disappear. So we need a visibility timeout. That is set timeout for 2 seconds. So after 2 seconds we want to set visible false, and immediately we want to set visible true. And then we need to clear the timeout. Clear timeout visibility like this. So we only want to show something is if visible is true. So let's do class name absolute and centered. So now we also need to handle so that the texture is actually changed when we press the digits. Actions from use keyboard. So in the store we have a set texture method. So let's finish that. We take a texture called set. We don't care about the previous. We just want to set texture based on the incoming texture. So let's look at use keyboard. We have texture 1 to 5. This is what we want to dig out here. So let's do a useEffect again. That will run for texture 1, texture 2. If texture 1. So now we need the set texture from the store. Set texture dirt. Okay, we'll call this dirt, grass, glass, wood, and log. So the actions will now contain props that are the actual names of the textures. So we'll call it pressed texture. So if any of these textures are true, then that texture will be the pressed texture, and then we can do if pressed texture set texture to pressed texture. Let's see, pressed texture. So let's see if it works. if I press 1, all right, let's debug. So if I press 1, dirt to be true. So that's great. So it works correctly in use keyboard, and in the texture selector, let's console log dirt. Let's see if we can get dirt to be 1. So one thing what we must do is add the texture selector to our app before we start to looking for console logs in it. So let's add it here. Texture. All right, so we get dirt false. We saw it there, and as I press 1, we got dirt true, and texture selector appears for 2 seconds and then gets removed. So it looks very promising. Active texture. All right, so here we have our textures as booleans. So let's create a mapping that will set the prop, which is the name of the texture, that will map from the name to the booleans. So then we can do object.entries, find key value. So we want to find a texture where the value is true. If we have such a pressed texture, we'll take the value from that. All right, so we get 5 booleans here, and we put them in a mapping. So we'll get dirt false, grass false, maybe glass true. And if glass is true, we will find the true texture, store that in pressed texture. So if we found a pressed texture, we get the key of that by taking the first element in that tuple. So let's see if it actually worked. Pressed grass, pressed dirt, pressed wood, and pressed log. So now I press glass. So this is the glass cube. Pressing dirt, and I get a dirt cube. So cool, we have a way of selecting different textures just using the keyboard. I don't know what happened with this cube. But let's continue building the UI to show the actual selections. So we already have a list of images with these. So let's import those images. Okay, so let's create a mapping here. Images. So we keep the name that they are called in the store to the actual image. Yes. So we need to loop these in a map here, images, and we'll do object.entries, images. So here we get key and source image. So we can return an image tag. Source is source, key is k. And now we need to check which one is the active one. And that we can do by adding a class name. So here we can do k equals active texture. If that is true, we add active, otherwise nothing. And let's have an alt prop, put the name of the texture. All right, so let's see if anything happened. So when I change the texture now, here we have an error. This should be an array. So now let's see what, oh, we got it. So when I change texture, the texture selector appears. So we should just make it bigger. Let's add a class. texture select. So we can do transform scale 10. It should be selector. There we go, that's bigger. Let's do maybe 5. And then let's handle the active also. So if we have an image.active there, let's do a border of 2 pixels solid red. So let's see if we can see which one is active. Yes, we can. Okay, so we between the 4 and the 5 we have the wrong digits. So that is probably because I typed them in the wrong order here. Alright, now they work correctly. Alright, let's see all our cubes. We have wood or log, we have wood, we have glass, we have grass, and we have dirt. Really nice. Let's remove this console log. Alright, so our cube type selector is done. The next thing on the agenda would be to save the world in local storage. So that is something that we can do inside of our store. So let's create some helper functions to talk to the local storage. So what we want to store in the local storage is an array. So we need to do JSON parse and JSON stringify to talk to the local storage. So let's create a helper function. Get local storage. So we take in a key and we return JSON.parse window local storage get item of key. So all we're doing is JSON parsing what we get from local storage, and let's do a similar function with set local storage. We take in a key and of course the value that we want to set, and then we do JSON stringify set item, and then we pass the key. Actually this JSON stringify should be just wrapping the value. Right, so now we have our helper functions. So when we first create the state, we want to do get local storage, and we can just make up a key here. We'll call it cubes. So we'll either get something or it will be empty. So we'll fall back to the empty array. So now we can implement these two functions. Let's start with just resetting the world. That would just be set, and then we just set the cubes to be empty array like that. That should reset the world, and then we have save world. So we call set just to get the current state, and inside here we just call set local storage. The key was cubes, and we store prev.cubes. So we don't need a load world function because that happens when we just reload the page. But we also need to create some buttons on the UI for this. Let's create a component called menu. So we want to access save world and reset world from use store. So state reset world. All right. So let's create some UI. class name of menu and absolute. We need save and we need reset. On click save world. Reset world. All right, let's import menu. So let's see where we have our menu. We have it, but it's down there, so we need to style it so it becomes in the top. So we'll do top 10 pixels, left 10 pixels. There we have them. All right, so let's try them out. We'll place a few cubes of different types. All right, we have a nice line here. Let's save it. So now it should be in local storage. We can verify that. Application, local storage, we have cubes, and there we have the cubes. So now when I reload the page, do we have any cubes? Oh, here they are. Really cool. So now we can persist it. Of course, we can also reset, but they are still in local storage. So if I just reload, the cubes will be there. All right, we are done with saving the world in local storage. But we have one more thing that would be nice to have. Hover state on cubes. I think it would be nice if when the cursor hovers a cube that they become a bit darker so that you indicate what cube you're actually hovering on. All right, let's keep track if a cube is hovered. Set is hovered. useState from React false. Now we can add some pointer events here. On pointer move, and we take the event stop propagation. Set is hovered true. And then we just do the same for on pointer out. And now we need to adjust the appearance based on the hover. So let's add color here. Is hovered. Let's make it gray. If they're hovered, we make them gray. Otherwise, we keep them white. But one thing that would be nice is if the glass cube would actually be a bit transparent. So we add transparent true to all the cubes. And then we do opacity, active texture equals glass. Then we do 0.5. Otherwise, we do 1. And this should be just texture. All right, so there we have transparent glass, and maybe it's a bit too transparent. Let's do 0.6. Really nice. Very cool. All right, so we're getting close to being able to build that house. And of course, transparent glass is a must for building houses. So you can watch outside. All right, I will quickly finish this house just to check it off the list. Should probably have a door. All right, we're inside the house. I think we can check it off the list. All right, we can say actually right now that we have fixed everything on our to-do list and even some more things that we had to add as we went on. For those of you that got this far, kudos to you. It's quite a long project. If you want to submit pull requests to this project, feel free. I will look at them and probably pull in many of them. So thank you so much everyone that watched. I hope you learned a thing or two about building 3D things on the web, and I hope you got inspired to try out to build something on your own. So please keep watching freeCodeCamp, continue to learn, and also you can check out my channel if you should want to. Bye now, thanks a lot for watching.